Hello everyone and welcome to Doc News Daily. In this episode, we will be discussing Wepi Cikan, an Indigenous sport, and the physics concepts behind it.
Wepi Cikan is a native Canadian sport which comes from the tribes of Saskatchewan. This was a sport with slingshots, which were often the property of small boys. This was a sport used to often develop their aim and coordination skills as they were applicable in hunting lifestyles.
This game is traditionally played with a sling that is made out of rawhide.
However, rawhide isn't too accessible for us, so using a piece of styrofoam, some cloth to cover it, and some rope has allowed us to create our own sling. The sling follows the exact idea as the traditional ones, where a ball or rock is placed in the middle, then is cupped and spun around to be thrown.
The object of the game is to throw rocks. The winner is the person who skips the rocks across the lake the most amount of times or throws the required distance in the least amount of tries.
The analysis of this project will consist of 5 main parts, which are then broken down into a further analysis on Earth, a planet with less gravity, and a planet with more gravity.
For a planet with more gravity, we'll be using Jupiter, which has a gravitational force of 24.79 meters a second squared. And for a planet with less gravity, we'll be using Mars, which has a gravitational pull of 3.711 meters a second squared. In Wepi Cikan, the ball is thrown around using a sling up top of your head in order for it to build up velocity. After that initial movement, once the ball is released, it becomes a projectile. The motion of the ball can be calculated and described using kinematic equations and concepts. Here I have a diagram of a projectile in motion. This figure shows both the horizontal and vertical components of its velocity. As you can see here, the horizontal velocity is always constant for projectile motion, as there are no forces acting upon it. Next, we have the vertical velocity. The projectile starts with an initial vertical velocity, and due to the force of gravity acting opposite of it, this force, or this initial velocity, decreases every time. And at max height, the velocity vertical becomes 0, and gravity starts to accelerate the object, or the ball, downwards, thus creating more vertical velocity downwards as it starts to increase here. This downward velocity is the same magnitude on the other side of its parabola as it is a symmetrical shape. As you can see here, this is a change in velocity and acceleration problem. Based on the information we were given, we can tell we need to find the change in acceleration and velocity. Thus here, we are able to draw our graph to show us what's happening. We can see it bounces at an angle 35 and leaves at an angle 30. We also know that the change in velocity is equal to v2 minus v1, or we can rearrange and find v2 plus negative v1. Thus, negative v1 plus v2 will give us our change in velocity, and we can use that to solve. Using the components from our v1 and v2, we can find a resultant velocity or change in velocity. As you can see here, we have our two triangles divided up to easily see them. We have decided to make up a positive number and right positive. And to find the component of each triangle, we know we have our v1, which is our hypotenuse. And using components, our sine and cosine, we can find the length of each one. We then add these components together in order to solve for a resultant triangle. Our final answer gives us 28.1425 meters a second. And using a tan function, we were able to find the internal angle, which would be up 4.4 degrees left, meaning our change in velocity is 28.14 meters a second, up 4.4 degrees left. The final part of this question is to solve the change in acceleration. This is simply found using the change of velocity divided by the change of time, which gives us 625 meters a second, and it would be the same angle, up 4.4 degrees left. Another example of a kinematics problem in Wepi Cikan is a resultant velocity problem. For example, if the ball is thrown at a speed of 72 kilometers an hour north, and there is a crosswind of 18 kilometers an hour from the east, what is the ball's resultant velocity? As you can see here, we have a relative velocity problem. We are given velocity of the ball with respect to the wind, and velocity of the wind with respect to the ground. And we know we must find the velocity of the ball with respect to the ground. Thus, by adding the two other components, the wind components cancel out, and we are left with the velocity of ball with respect to the ground. Thus, by using Pythagoras' theorem, we were able to find our missing side length, which is the hypotenuse. We can find out that our missing side length of the ball with respect to the ground, the velocity, is 20.615 meters a second. And using one of the trigonometric ratios, we can find that our angle is north 14 degrees west. However, if we were to play this game on Mars, for instance, with its weaker gravitational pull, a perfectly thrown Tiki-Chiwan ball would travel roughly 2.5 times further on Mars compared to on Earth. Mars has a smaller radius and mass compared to Earth, which means there is a smaller gravitational pull on the ball to the center of Mars. This would make the game significantly easier compared to on Earth, as less velocity is needed to travel a great distance. As discussed with the different gravitational forces on different planets, the balls will all achieve different heights and distances. As you can see here on this graph, we can see that on Mars, the ball achieves the greatest height and distance due to its very low gravity. And finally, we have Jupiter. As you can see, this is a very small arc, as the force of gravity acting down on the ball on Jupiter would be immense, meaning that this ball would not travel very far and almost plummet straight down.
The first topic we want to cover is free body diagrams of the ball throughout the spinning of the ball and the projectile. The ball is swung horizontally above the head of the player. Gravity acts down on the ball, and the normal force is perpendicular to the surface of the slingshot. In this picture over here, you can see that the force of gravity is acting down and the normal force is acting to the right. Due to the unbalanced forces, there is inwards acceleration on the ball. This force causing the ball to move in a circle with velocity is called centripetal force. When centripetal force is removed, the object moves along a tangent to the circular path with speed, which is when it becomes a projectile.
The second free body diagram is of the ball when it is released from the slingshot and is in the air. The horizontal speed of the projectile is constant for the duration of the flight. Horizontally, the ball travels at a constant speed because there are no horizontal forces acting on the ball, assuming air resistance is negligible. Vertical motion of the projectile is only controlled by the force of gravity acting down on the ball. This means that the net force is not zero and the ball will accelerate downwards, as this is the only force acting on the ball.
I will now be talking about Newton's laws and how they relate to the game of Wepi Chicken. Newton's first law states that an object will remain in constant motion or rest until acted upon by an external force. When the ball is spun horizontally above the head, it pulls outward on the string. This force is called the centrifugal force caused by the inertia of the object where it wants to follow a straight line path. However, by applying a continuous sideways force on the object, it can overcome inertia and cause the object to take a curved path for as long as that force is applied. That applied force is called a centripetal force. Newton's second law is the net force is equal to the mass times the acceleration.
Newton's third law states that for every action force, there is an equal and opposite reaction force. Centrifugal force is equal and opposite to the centripetal force that acts on the object and causes it to move in a curved line.
We will now be talking about the role that friction plays in the game of Wepi Chicken. When the ball is in its circular spin above the thrower's head, the force of friction plays an important role as the force of static friction prevents the ball from slipping out of the slingshot. We will now be talking about how the forces acting on the ball would differ on a planet with less gravity such as Mars and on a planet with more gravity such as Jupiter. On Mars, since there is less gravity than there is on Earth, you and everything around you feels much lighter. This means that when the object is thrown, there is less of a pull on the planet compared to the Earth, meaning the initial trajectory of the object is a lot smaller. On Jupiter, since there is more gravity than on Earth, the time it would take to accelerate the ball down would be much faster than on Earth and Mars especially.
To find the centripetal force acting on the ball while it's in rotation, we must use the equation mass times velocity squared over radius. The radius of the rotation is 0.44 meters, the ball's mass is 0.058 kilograms, and its velocity is 13.89 meters per second. When we input those values into the equation mv squared over r, we see that the centripetal force acting on the ball in the spin is 25 newtons inwards. To find the force of friction during the spin, we must remember that the force of gravity is equal to the static friction. The force of gravity is equal to the ball's mass times acceleration due to gravity, and the force of static friction is equal to that magnitude.
To calculate the force of tension acting on each rope, we must remember that the centripetal force is equal to the force of tension. The centripetal force is 25.427890002 newtons. So the force of tension is 25.427890002 newtons. To find the force of tension on each rope, we will take that value and divide it by 2.
For this problem here, we can tell we must calculate the instantaneous velocity of the ball in a circle. Here we know that force centripetal is equal to the force net, meaning force net is equal to mass times acceleration centripetal. And we can substitute this equation 4 pi r squared times f squared will give us the acceleration. Thus, we are able to rearrange our equation and find velocity. And here we found that our velocity is 4.61 meters a second. Since it is an object in a centripetal motion, we know that the force would be directed perpendicular to the center.
In this section of our video, we will be talking about impulse, momentum, and energy. What is momentum? Momentum refers to the quantity of motion that an object has. Momentum can be defined as mass in motion. We will now talk about the momentum in collisions. In an elastic collision, not only is momentum conserved, but also kinetic energy. In an inelastic collision, momentum is conserved, but the total kinetic energy of the system is not. In the real world, there are no purely elastic or inelastic collisions. When the ball lands after being thrown by the player, it bounces off the ground. This collision is not elastic as the kinetic energy of the ball is not equal before and after the collision, as kinetic energy is lost to heat and sound energy.
Conservation of energy. Energy is never created, nor is it destroyed.
it just transforms into other forms of energy. In this situation, as the ball is being spun above the player's head, it has kinetic energy with rotational kinetic energy as part of its total kinetic energy. Just after the ball is thrown, it has kinetic energy. When the ball is at its max height, it is still moving forward because only the vertical velocity is zero, meaning it mostly has potential energy with some kinetic energy. The ball then bounces off the ground with elastic potential energy, but energy loss occurs such as sound and heat energy.
On Mars and Jupiter, all of the things said would apply. The only thing that would change in energy, momentum, and impulse is that on Mars, less energy would be lost as there is much less of a pull on the ball than on Earth and Jupiter. More energy would be lost on Jupiter as the greater force of gravity causes for the ball to have almost no rebound height after landing, with most energy lost due to elastic potential.
Of the planets we chose to investigate, Earth, Mars, and Jupiter, none of these have an electric field. However, they all do have magnetic fields. Earth is one of two planets in our solar system who has a magnetic field generated by the movement of liquid metal at its core. Earth has a magnetic field of 25 to 65 microteslas. Mars does not have a conventional magnetic field. Instead, Mars has magnetic crustal fields that create fields of magnetism if it is oriented properly. This force is very weak at 1500 nanoteslas, or about 1.5 microteslas. Jupiter, the largest planet in our solar system, also has the largest magnetic field. Jupiter's magnetic field, which is generated from its outer core, which consists of liquid metallic ionized hydrogen, and has a very large magnetic field, which is not exactly known. The easiest way to incorporate electric fields into Wepi Cikan is to set up a set of parallel plates and a charged ball or particle. Based on the orientation of the plates and the particle, we will get different results, and the ball will either go up or downwards. For this first setup, where the positive magnet is on the top side, we have an electron, which is a negatively charged particle, and a proton, which is positively charged. Based on the laws of electric fields, we know that this electron will start to shift upwards and have an upwards trajectory, which would look something like this. This is due to the attraction to the positive plate as an electron, and the repulsion of this bottom plate. The opposite is true for the proton. We know that it will repel the positive and be attracted to the negatives, and thus will also follow a path somewhat like that. Just using magnetic fields wouldn't be as useful, as we know that charged particles follow a circular motion when in a magnetic field. We can find this out using right-hand rule or left-hand rule if it's an electron, where our thumb is the direction of the velocity, our fingers are pointed in the direction of the magnetic field, in this case it would be inward, or in this case it would be outward, and our hand is the force indicated, which we know is perpendicular to the velocity, and this causes the circular motion. The most useful one to use would be a combination of both magnetic and electric fields. This would be called a velocity selector, where the force magnetic is also equal to the force electric. Since we know the forces are equal, this object will accelerate very quickly forward, and this concept can be used to modify our game to make it very fun to play. For this first question here, we have an electric field, and we are required to calculate the acceleration of a particle through this electric field. We know that our electric force is equal to our force net, meaning our equation of Fe is equal to ma. Thus, we are able to sub in for Fe epsilon q. However, we don't have epsilon, but on the other hand, we do have voltage and distance, meaning we're able to sub in epsilon for V over d. Rearranging our equation, we can solve for our acceleration. Our final problem here is a velocity selector problem. This is where our magnetic force is equal to our electric force, as the object is able to accelerate through this and go at a very high speed. Since these two are equal to each other, we are able to derive their equations in order to solve for velocity as needed in this problem. We are able to rearrange for velocity, which becomes voltage over distance times our magnetic field strength. And using the numbers we were given, we can find that our velocity of the particle or the ball as it exits will be 5,800 meters a second.
Today I'll be discussing celestial mechanics with respect to the native game Wepi Cikan. To begin, a gravitational field is the collection of vectors in space that determine the magnitude and direction of a gravitational field. The gravitational field exerts a force on all objects with mass. In Wepi Cikan, there's a gravitational field acting on the player and on the ball from the Earth. The gravitational field strength is the force of attraction of an object at a certain point due to the magnitude of the gravitational field. To calculate the gravitational potential energy of the player, which is Julian in this case, we're going to take the universal gravitational constant, multiply that by the Earth's mass, and multiply that by Julian's mass plus the mass of the tennis ball, and divide that all by the radius of the planet. Once we input our values and solve, we see that Julian has a gravitational potential energy of 4.40 times 10 to the 9 joules when he is at rest on the Earth's surface. To calculate the gravitational potential energy of the ball just after it is released, we will take the universal gravitational constant, multiply that by the Earth's mass, and multiply that by the mass of the tennis ball, and divide the whole thing by the radius of the Earth plus Julian's height. Once we input our values and solve, we see that the ball has a gravitational potential energy of 3.63 times 10 to the 6 joules right after it is released. Now, the binding energy of an object is the amount of energy required for an object to escape the gravitational field. In this case, it's the ball trying to escape the gravitational field of Earth. Binding energy can be represented by the equation E total plus binding energy is equal to 0. For an object to escape the Earth's gravitational field, its total energy must be greater than 0. When the player is standing on the Earth's surface, their total energy is equal to their gravitational potential energy. The player begins to swing the ball around their head, and once the ball is released, the ball's total energy is equal to its gravitational potential energy plus its kinetic energy. To find the ball's binding energy, we'll take the equation stated previously and rearrange it so that binding energy is equal to the absolute value of the total energy. Once we input our values and solve, we see that the binding energy required for the ball to escape the Earth's gravitational field is 3.6 times 10 to the power of 6 joules.